Hello and welcome to another Algebra 1 video tutorial. In lesson 12.6 we'll be looking at which quadratic expressions are factorable, because we know that some are not. So we're looking at a quick way to see if it is factorable over the integers or not. So our goal will be to use the discriminant, b squared minus 4ac, and the fact that when a, b, and c are integers, the discriminant must be a perfect square or 0 in order for ax squared plus bx plus c to be factorable over the integers. So you've seen 4 ways to find real number values of x such that they satisfy the quadratic equation equals 0. 1, you can graph and look for its x-intercepts. 2, you can use the quadratic formula. Number 3, you can try to factor it and use the zero product property. And number 4, you can set f of x equal to that equation to 0 and then look for values of x such that f of x equals 0. Alright, so 1 and 2 will always work. We can graph it as long as we find the right window. We can get an estimate. And 2, the quadratic formula always works. 3, factoring isn't always possible. And then so that means we can't necessarily use the zero product property. And same with 4. It's not always easy to find such values. But 1 and 2 are tried and true methods. Alright, so let's consider 9x squared plus 14x minus 8 equals 0. So when we use the quadratic formula, we always find the discriminant, and that's what we're going to use today, is the discriminant to see if it's factorable, which is nothing new as far as finding the discriminant. Remember, the discriminant is b squared minus 4ac, and in this case a is 9, b is 14, c is negative 8. So we're going to go 14 squared minus 4 times 9 times negative 8. And that would give us 484. 484 is a perfect square, so that makes the quadratic formula quite nice. Remember, in the quadratic formula, we do the opposite of b, plus or minus the square root of the discriminant, which in this case is 22, over 2a, so over 18. Now, in this case, we're going to get negative 14 plus 22. That's going to be 8/18, which we could divide that by 2 and make it 4/9. Then if we went negative 14 minus 22, that would give us negative 36 over 18, which is negative 2. Those are the two solutions that make sense here, and that's using the quadratic formula. Now, since this is a perfect square, and these are rational answers, that means that this also factored. And what would it factor? Well, if negative 2 is one factor, I know that one of the factors would have been x plus 2, because with the zero product property, negative 2 is one of these quantities that makes it 0. Well, if 2 is 1 and I need 9x squared, and if x is the other factor, I would have to have this be 9x. 2 is this factor in the second term, and they multiply to be negative 8, so this would have to be a minus 4, hence the 4/9. See how that is 9x minus 4. So then using the zero product property, we get the same two answers. But I was working backwards, knowing the answers, and using that to help factor it. So this would have factored into 9x minus 4 times the quantity x plus 2. And you could use that. If you would have tried to factor this first, you'd have got this. And then you could use the zero product property to get these two answers. All right, so that leads us to the discriminant theorem. So when a, b, and c are integers and a isn't 0, either all 3 of the following conditions hold or none of them hold. So number 1, b squared minus 4ac is a perfect square. Number 2, ax squared plus bx plus c is factorable over the set of polynomials with integer coefficients. And number 3, the solutions are rational numbers, like we just saw in the last example. All right, so is 10x squared minus x minus 24 factorable into polynomials with integer coefficients? Well, we'll find the discriminant, and in this case, the a is 10, the b is negative 1, and the c is negative 24. So we're going to go negative 1 squared minus 4 times 10 times negative 24. It's going to give us 1 minus a negative 960. So 1 plus 960, which is 961, and 961 is a perfect square, so this will be factorable. Now, I'm going to use the values of the solutions, if this was equal to 0, to help me factor this, because 10 has a fairly 1 and 10 or 2 and 5 for factors. 24 has quite a few factors, so this might not be the funnest to factor, but we know it will factor with integer coefficients. So with the quadratic formula, we do the opposite of b, plus or minus the square root of the discriminant. So 31 in this case, over 2a, so over 20. So 1 plus 31 is 32 20ths. We can divide that by 4 and make it 8/5. And 1 minus 31 would be negative 30 over 20, which would be negative 3/2. Now, how can you use those answers to, if this was equal to 0, to help us factor this? Because these are solutions to the quadratic formula if it was equal to 0. Well, we would have 8/5. So using the zero product property, if this was equal to 0, I would know I'd have a solution of 8/5. So that means to get this, I would have had to add 8 and divide by 5. So that means I know that would have to be 5x minus 8, right? If you add 8, right? What I'm thinking about is if 5x minus 8 equals 0, I'd have to add 8 and then divide by 5. So that's where the 8/5 comes from. So undoing that, I know that added 8 divided by 5. So the factor would have been 5x minus 8. Now knowing the rest, the other one has to be a 2x and a plus 3, right? Well, that's because subtract 3, so the opposite would be add 3, and divide by 2, so the opposite would be multiply by 2. But if you can get one of these and you know what it originally was, then you can get the other two factors. So yes, it factors, and here's what it would factor into. All right, is the polynomial 5x squared minus 1 minus 3x factorable? Well, the first thing we do is rearrange this so we can pick out our a, b, and c values. So this would be 5x squared minus 3x minus 1. Okay, find the discriminant. So a is 5, b is negative 3, c is negative 1. So negative 3 squared minus 4 times 5 times negative 1. So that gives us 9 minus a negative 20. It's really 9 plus 20, which is 29. So is this factorable? 29 is not a perfect square, so this is not factorable. So not factorable over the integers. Everything will factor if you can use non-integer values, but we are using integers. Alright, so what can be learned by applying the discriminant theorem to the quadratic equation x squared minus 8 equals 0? Well, we'd find the discriminant if we were trying to solve this, and we'd get 0 squared minus 4 times 1 times negative 8, which would be 0 minus a negative 32, which is 0 plus 32, which is 32. Well, that's not a perfect square, so that means this is, first of all, not factorable, and we know it also does not have integer solutions. So 32 is not a perfect square, so x squared minus 8 cannot be factored into linear factors with integer coefficients, and we also know the solutions to this would be non-integers. They'd be irrational. Not just non-integers, they'd be irrational as well. Okay, now, not factorable with integer coefficients, because I'm going to show you this will factor if I don't use integer coefficients. This is a difference of squares, so this would have been x plus something and x minus something. And it would have to be the same thing. Well, it's the square root of 8 and the negative square root of 8. So this actually factors into this, but not with integer coefficients. So I can factor this if I don't use integer coefficients. And as far as the solutions, I wouldn't even need the quadratic formula because I would just add 8. I just have x squared. So I'd add 8 to both sides. Try that again. X squared equals 8, square root it, so I'd get x equals the square root of 8 and the negative square root of 8. So square root of 8 is not a perfect square, and so that means that that's not a rational solution. All right, solve p squared minus 4p plus 7 equals 0 by any method. You may want to pause the video and give this one a try and see what you come up with. All right, what I would do first is find the discriminant, because that can tell us a lot about the answers. Okay, so I do, it's already set up. A is 1, B is negative 4, C is 7. So negative 4 squared minus 4 times 1 times 7, which gives us 16 minus 28, which is negative 12. Well, first of all, we know negative 12 is not a perfect square, but it's not even a positive number to start with. So the discriminant is negative, so that means there's no solution. First of all, it's not factorable. But even further, there is no solution because the discriminant is negative. All right, so that wraps this up. Your assignment will be 12-6, page 752, numbers 2 through 18 evens. Thanks for tuning in, and we'll see you next time.